In this video, we'll look at vector operations of multiplication. So far, we've seen several operations already. We've looked at scalar multiplication of a vector, which is some constant times the vector which scales it or stretches it. We've seen vector addition, so u plus v, and vector subtraction, u minus v, which has a resultant vector. And today we'll look at the dot product of two vectors, u dotted with v, and we'll look at the cross product of two vectors, u cross v. So the dot product of two vectors, u and v, can be given by the equation u dot v equaling the product of a times c, so the product of their x components, plus b times d, or the product of their y components. Now it's important to note that the dot product will only work for two vectors that have the same number of components. So in R2 or R3 or any n-dimensional vector, but they have to be the same number of dimensions. And you'll notice that the dot product results in a scalar. It results in a quantity. A times c plus b times d is going to give you a number, not a vector. So if we look at an example of the dot product, well, let's determine the dot product of u dotted with v. It's always good to draw a diagram, so here we have u and v. And we know that u dotted with v will be 2 times 0, product of their x components, plus 2 times 3, which is the product of their y components. So 0 plus 6, or u dotted with v is equal to 6. Now, there's an alternative equation for the dot product, and we use the law of cosines to develop this. We won't go into this in this video, but if you're curious, you can look at this later. So the dot product of two vectors u and v then can be given by the equation u dotted with v, which equals the length of u times the length of the vector v times the cosine of the angle between those two vectors. And often this is a useful equation if we want to determine the angle between two given vectors using this information. So let's look at our example again. So let's say we have u and v, and I want to determine the angle between those two vectors. Well, I know my equation u dot v equaling the length of u times the length of v times the cosine of the angle between them. And I want to solve for that angle. Well, I know u dot v was 6 from our prior calculations. I can compute the length of u, so the length of u is the square root of 8, and the length of v I can also compute, which is of length 3. So if I go ahead and I put those into my equation, I have the dot product is 6 equals the square root of 8 times 3 times cosine of theta. Now I isolate cosine of theta by itself, and I take the inverse of cosine in order to determine theta. So theta in this case is 45 degrees. And if we look at that on our graph again, it does appear to be that it's a 45-degree angle between the vectors u and v. So in addition to the dot product as a form of multiplication, there's also the cross product. Now, the cross product is defined only for three-dimensional vectors. And unlike the dot product, this actually results in a vector. And if we're given two vectors u and v, then I can define the cross product as the following formula. So u cross v is y1 times z2 minus y2 times z1. That's the x component, x2 times z1 minus x1 times z2, and then that's the y component, and the z component will be x1 times y2 minus x2 times y1. It's a rather complicated formula. I don't memorize it, but it's use cofactors of determinants. That's how we actually get it. We won't go into that in detail here, but the length of u cross v is also the length of u times the length of v times the sine of theta. Now, the cross product has an interesting formula, but it has a very easily understandable geometric interpretation. Here we have an applet that helps us understand the geometrical interpretation of the cross product. So here you can see I'm in R3 because, again, cross product is defined for vectors in R3. Let's say that this is my vector A, and this green one here is my vector B. And you'll see that they create this plane or this parallelogram between the two. So between these two vectors we have a parallelogram that it creates. You can stretch it out, you can sort of see here. And the cross product, the length of it is the area of this parallelogram. So you'll see here that this pink area here is the same as the distance or the magnitude of the vector in red. And the vector in red, the direction is determined by finding the normal vector, or the vector that's 90 degrees, from these two vectors, from the plane that it creates in these two vectors. So the cross product has a more easily understandable geometric interpretation. It's in the direction that's normal to the two vectors, the plane of the two vectors, and the distance of it is the area of the parallelogram that is created between these two. A special thanks to our sponsors for helping create these videos.